So yeah, thank you to the organisers for arranging such a nice conference and getting me out into the sun. So yes, I'm going to talk about how uncertainty clarifies observables from scattering amplitudes. So if you were lucky enough to be in Julio's talk yesterday, he will have already justified for you exactly why scattering amplitudes are interesting for thinking about problems in gravity. Right. Yeah, so we can so the point is that we can build amplitudes without necessarily going through the typical machinery of quantum field theory, such as path integrals and Lagrangians and that sort of stuff. There's lots of interesting tools that we can use to, for example, recycle amplitudes from gauge theory, there's unitarity cuts to compute loops, there's recursion relations, etc. As we saw in Jeffrey's talk earlier, numerical relativity is expensive, but theorists are very cheap, I assure you. And this wisdom by Feynman, just that we should know other ways to think about things if we're going to be good theoretical physicists. The only problem is that if we're really interested in classical gravity effects, amplitudes are quantum. So we need to go from, we need to find a way to extract the classical physics. So what we're going to be thinking about is two particles in some initial state in the far past, evolving to two particles in the future, plus some emission of a gravitational wave. Or just a graviton or whatever. And we're going to be in the classical domain, meaning we're going to be thinking about initial separations far bigger than the Compton wavelengths of any of the particles. And the question is, how do we efficiently extract classical observables from these quantum amplitudes? Amplitudes, being quantum, have uncertainty built in. So this is the general Heisenberg uncertainty formula, and it basically tells you that if you've got two operators, A and B, you should expect them to have an uncertainty proportional to their commutator squared, where this delta is the variance of the operators, or of the operator. There's delta A here. And classical physics is pretty much the statement that this variance vanishes, or is at least negligible, relative to the scales that you might be interested in. What's interesting for our purposes is that minimal uncertainty gives you a kind of exponentiation, right? So a state that minimizes this bound looks like this. So let's think about why that might be. So we're going to think about the harmonic oscillator, because everyone likes the harmonic oscillator. And if we think about position and momentum operators of the harmonic oscillator, then we can write down these creation and annihilation operators in some funny units, because the creation and annihilation, the operators obey the algebra that they are expected to, because they inherit the algebra from X and P. And X is given, roughly proportional to A plus A dagger, and P is roughly proportional to A minus A dagger. And the state that I showed earlier, the exponential state, is an eigenstate of the destruction operator, annihilation operator. And we find that the expectation value of X or the expectation value of P are related to the real or imaginary parts of the eigenvalue. And we can see that if you plug these guys in, you'll find that they do indeed exactly saturate the uncertainty bound that I had on the last slide. So one well-known example of amplitudes and exponentiation, thankfully Carlo just introduced to us in the last talk, is the iconal, which roughly says that if you've got a scattering amplitude in B space, impact parameter space, it exponentiates in this nice way. Now, roughly, you can think of this as you've got two high energy particles exchanging every possible combination of gravitons, low energy gravitons, and you resum these guys all up in impact parameter space, and you'll find that they give you this kind of exponential structure. And you know, it's a Fourier transform of the momentum space amplitude, but it's specifically restricted to this plane that's orthogonal to P1 and P2. Right? This very efficiently gives you certain observables, such as the scattering angle and the classical impulse, for example. And it being classical, the uncertainty must be minimal, right? In the sense that I talked about in the last slide. So let's look into that a little bit. So any of the scattering amplitudes that I just had on the last slide can be expanded, well, in gravity specifically, can be expanded into these sub-amplitudes, which we call fragments, which are kind of labeled by their h-bar scaling. So there's some overall 1 over h-bar to the k factor out front, and then there's a sum of different h-bar weighted amplitudes. And the iconal itself can also be expanded in a order g expansion in the exponents. And we can just take the exponential on one side and the amplitude on the other and compare them. And we find that we get a relationship like this. So in the first case, it's just telling you that the 0th order iconal phase is related to the tree level amplitude. The 2nd order iconal phase is related to the one loop, but there's also this 1st order iconal phase squared, which is also related to the one loop. So really what this is telling us is that somehow there's a one loop amplitude that must be related to the square of the tree level amplitude. So it's relating loop amplitudes and tree amplitudes, right? And that's, I claim, is an example of reduced minimal uncertainty. So let's have a look why. So we can consider demanding minimal variance of just, we're thinking about momentum. We're thinking about momentum states with definite momentum. So we can choose an eigen operator, P, and look at the variance of a couple of those guys. But we're also thinking about scattering amplitudes. So we're going to evolve those guys with the S matrix, which is unitary operator. It takes us from the far past to the far future. So we're going to look at the far future expectation value of two momentum operators. And the statement of minimal variance means they have to factorize into expectation values of two individual momentum operators. So we can expand S into the usual 1 plus IT, where T is this transition matrix that defines the scattering amplitudes for you. And these guys here are just 4-point scattering amplitudes. So this tells us that we've got a relationship between a 4-point amplitude and two 4-point amplitudes, right? Now, if we just count powers of G, that tells us that the one loop amplitude has to be related to the square of two tree level amplitudes. And this is exactly what we just saw in the iconal, for example. And of course, you can put in more P's and find more relationships between all sorts of loops and lower loops and all that sort of stuff. Now, if we're going to look at minimizing variance, it's useful to have a state that we can do that with. So we're going to build an iconal finite state. So we're going to start with what's known as the K-Mock state, which is just to say it's a state with a wave function which makes the classical limit well behaved, makes the location of our particles not completely spread out all over the place. And B here is the translation of one of the particles initially with respect to the other one. And we're just going to have a two particle initial state. We're We're going to evolve it with the S matrix, just like we did before. And we find that we get this 4-particle amplitude, where now there's a delta function involving these funny p's. Q here is the transferred momentum. And we recognize this guy from the formula I had a couple of slides back as being the Fourier transform of the iconal phase. Right? So now we can write S acting on psi as being, the differential integral plus a Fourier transform of the iconal phase and some final 2-particle momentum state. Okay. Oops. All right. Okay. So now I want to look at some observables. Now, for the next few slides, we're just going to be interested in the waveform, which is related to the Riemann tensor. But more generally, we might be interested in the impulse or the change in classical spin. So the impulse is related to the momentum operator that we just looked at, and the classical spin is related to the Pauli-Lubansky operator. Now, we'll focus on the Riemann tensor operator for the time being. So we're just going to look at it at linear order, expanded into graviton operators. Graviton operators obviously create gravitons. And roughly speaking, this thing is just proportional to A plus A dagger times some tensorial stuff that's not going to be particularly important for this discussion, so I'm going to leave it out. And we're going to look at when this variance is negligible, which signifies that we're looking at classical physics. So using that, we can just plug that guy in and evolve with the S matrix operators again. And we find by, again, looking at leading order, we find that this puts a constraint on amplitudes. But now these are amplitudes that radiate. So this guy up here has got 2 powers of, say, A or A dagger. This means it creates 2 gravitons from our 2-particle state. So we have 2 particles going to 2 particles plus 2 gravitons. This is a 6-particle amplitude. But this guy on the right-hand side only has 1 A or A dagger per expectation value. So it's related to a 5-particle amplitude. So 2 to 2 plus 1 graviton. And schematically, that's telling us that we have a 6-point proportional to 2 5-points. But again, if we power count in G, we find that you have to have a 1 loop on the left-hand side at lowest order and 2 trees on the right-hand side. This also tells us that the 6-point tree must vanish in the h bar goes to 0 limit. So the 6-point tree is quantum, whereas the 6.1 loop is the guy that's classical in this case. And you also see this other paper where they show that. Okay, so we can also consider mixed variances where we think about, different kinds of operators taking their expectation values and again demanding this factorization condition that minimizes uncertainty. So as an example, we can take a Riemann tensor with a couple of momentum operators, demand that they factorize, and we find that the 5.2 loop must be related to the 5-point tree and a couple of 4-point trees. And there's an infinite number of these relations. You just put more p's in, more momentum operators, and just keep doing this for, until you get bored, and you'll end up with however many relations you like. Diagrammatically, that might look like this. Now, you can recognize that this guy on the right-hand side here, is just all of the 4 points that you can think of, and this is, you might guess that this comes from just the iconal that I showed you first. You might think, okay, a really dumb guess would be to just say, well, it's just a 5-particle amplitude multiplied by the iconal. We can do better than that, so let's do that. So I showed you before that, these minimal uncertainty states that saturate the uncertainty bound are useful. And in quantum field theory, we can define these. In fact, we can define these for a 2-particle momentum state. They define like this. It's roughly the same as the previous guy, but it's just integrals and stuff. And that's useful for us because that means that if we put in, for example, we look at the same variance that we asked for before, it automatically is going to be order h bar if we use these particular states, right? And this leads to a proposal for the S matrix for states with radiated gravitons, or indeed photons or whatever. Might see it looks very similar to the stuff that Carlo just talked about. Okay, so this is just a kind of minimal proposal. There's no, we haven't proved it or anything like that, but you know, we should at least show that it passes some non-trivial tests. So let's do that. The first, very obvious thing that it's going to do is it's going to give you the all of the conservative dynamics if you just take the overlap between the two particle state, because it can only enter at minimum, because it's got a creation operator in the exponent, minimum at, well, g to the 3/2. So we can look at an overlap with a, you know, a 3-particle state, 2 scalars and a graviton, let's say. And this guy is correctly proportional to the 5-point tree. Similarly, we can look at the next order, and this gives us exactly the required subtractions that minimize the uncertainty. And similarly, you can go to g to the 7/2. Okay, so far so good, but we should look at something a bit more non-trivial. A bit more non-trivial is the radiation reaction. So we want to compute the impulse for that. So we're going to look at the impulse of particle 1 by putting in a P1 operator acting on our state. And we're just going to look at just the commutator acting on its own. Commutator acting on its own, basically the P1 just pulls down a final state. So P1 acting on the final state, so acting on S, acting on the state, just pulls down a P1 prime. And we can turn this, because of the e to the I P1.x, we can turn this into a derivative with respect to x1. And then we can integrate by parts and turn it into a derivative on the iconal phase and the 5-particle amplitude. And so this, in one case, it pulls down, you know, derivative of the iconal phase. In the other case, it pulls down the derivative of the 5-point amplitude. But notice that the iconal phase is multiplied by a 2-particle state now, whereas the 5-point amplitude, or the derivative of the 5-point amplitude, is multiplied by a 3-particle state because of the creation operator in the exponent. By the same token, we can compute the bra, which just means, you know, in one case, we're just going to have the P1 prime, P2 prime states, the 2-particle states. And if we want a 3-particle state, which we'll need for if we want to see this radiation, we have to expand the 5-point amplitude. So we get 1 copy of the 5-point amplitude as well. Weird. So the conservative piece then is just given by, okay, these large brackets hide all of the details of all the integrals that we've got to do as there are. But in fact, in this case, we can do them by stationary phase and get an all-order result, which is this Q star, which is the classical momentum, classical exchange momentum. Radiation reaction piece, unfortunately, I don't know how to do the integral, all the integrals required for this in all generality, but we do see that it enters at least at the lowest order of G cubed, and we can plug in, you know, the lowest order guys, and we show that that matches perturbatively. But there's a curiosity, which is something that Carlo was talking about earlier, which is that our proposed state had no normalization, right? So I showed you earlier that the coherent states or minimal uncertainty states have this e to the minus alpha squared in front of them. But our proposal doesn't have any normalization like this. And the only way that can be is if the normalization is part of the iconal phase, which is exactly what Carlo was saying, that if there's an imaginary part of the iconal phase, then it exactly gives you this radiative piece. So the imaginary part of the iconal phase must be proportional to this normalization, which is proportional to the 5 tree squared. Okay. So we also have a proposal for spin, which is where now we start by thinking about a state with spin. So, I have a state where now my creation operators have got some spin index, something about like Schwinger bosons or something like that. And the scattering amplitude now has spin indices, when you take the overlap of some of these states. So this immediately motivates a guess for the iconal, which is just that the iconal now has spin indices itself, being a Fourier transform of this guy, and then it's just contracted with the state on one side and some vectors on the other. And as I said a few slides back, we want to look at the Pauli-Lubanski operator, because this is the thing that if we take the expectation value and the classical limit, you should get classical spin. So we plug this guy in, churn through the details, and we find, again, a bunch of integrals and whatever, but ultimately this structure of an iconal phase multiplying a commutator of this classical spin vector, so this S mu is the classical spin vector, commutator with the iconal phase, or the iconal exponential, plus this spin vector evaluated on the classical impulse. So delta P here is the classical impulse, right? And given this structure of the commutator and the exponent, we can use the BCH lemma to expand this guy out. And we find that taking the classical limit, this ends up being, it should definitely be a mu on that S1. This ends up being the spin vector evaluated on the impulse, plus a bunch of Poisson brackets involving the spin vector and the iconal phase. And this is kind of a nice result from this section. So at lowest order, we can just take, this iconal phase, which just comes from the tree level amplitude. And we can plug this into the impulse, and we find that it correctly reproduces the classical impulse as expected. And we can use this classical impulse and plug it into the calculation for the angular impulse. Plug this guy, and we do find that indeed, again, you get the same, you get the expected results. So yeah, just to recap slightly what I've been trying to tell you. We've got a minimal proposal for black holes plus radiation in the form of this exponential of the iconal phase and an exponential of, roughly speaking, a 5-point amplitude multiplied by a creation operator. We've shown that it passes some non-trivial checks, but there's definitely more checks that we need to do to show that it really is a decent proposal. We've also got a proposal for spinning classical objects. And this again needs plenty of checks, but we've done some minimal work. Now we can think about what's next. So, as I just said, there are lots more things that we need to just check with these proposals, right? Spin beyond the probe limit, spin squared, etc. We saw some nice talks over the week about high dimensional operators and effective field theories, and there's no reason why we can't explore that regime a little bit as well with these proposals. We need to go to higher orders in G, where things like tidal effects become important, and memory, and we've seen some nice talks about that this week. There's some nice work on getting bound states from hyperbolic orbits by looking at analytic continuation, stuff like that. It'd be very interesting to explore that. Very obvious thing to do is to try and combine our proposal for the spinning iconal with our proposal for radiation and see if that makes any sense. And it also makes sense to look at radiation reaction beyond G cubed and go to higher orders and see what might be lurking there. I see I've gone a little bit fast, but that is everything I wanted to say. So thank you.
Well, when you finish a little early, it's just more time for great discussion. So thank you very much for that great talk. Any questions? Yes.
I'm interested in the equation you had a few slides ago, where you got the spin kick from the iconal phase. Yeah, that's the one.
Yeah.
I'm just sort of interested in what the validity on this is. This higher orders in G? Is this spin on both bodies? Is this
So this is just
line spins?
So this is just one spin and one scalar.
And in the probe limit.
Yeah.
Or yeah.
But to all orders in G in principle, yeah. In this expansion underneath, you can go.
And I can just imagine that it continues with the same pattern to higher orders, like a 6 with the next term, for instance.
Sorry?
Can I just imagine that the series
on
continues?
The bottom? Yeah.
With like a 6 for the next term, for instance. Yeah.
Yes, there's a question here from Jan.
Follow up, how is your Poisson bracket defined there?
As 1 over h bar times the commutator with the h bar goes to 0 limit. Sorry?
Maybe I'm misunderstanding, but S1 and chi, is that not scalar at this point? I mean,
yes, they are. Yes, now they are.
But commutator is, I mean, it would be 0.
Well, this guy is a commutator. So
yeah. No, I meant down there, your final formula.
Are those the classical Poisson brackets?
Yes, yeah, classical Poisson.
But in X and P or what?
What are your conjugate variables? X and P, something else?
Yeah, no. So the sort of algebra, if you like, would be S1. Well, yeah, 2 spins would give you like a Levi-Civita with some other spins, a P. So it would inherit the algebra that you get from the commutator. So, the Poincare algebra or whatever, it would inherit that, but the classical version for the Poisson bracket.
Yes, it looks like Justin has a question.
Thanks. Thanks for the great talk, Nathan. Just to clarify a little bit more, these Poisson brackets, you're saying they only act on spins. Like there are maybe impact parameter momenta in there, but they don't touch those. They just take 2 spins and give this Levi-Civita times spin, like you said.
So you're asking if I have something like S1 and then a function of the impact parameter.
Or, well, like Jan was, if you had a momentum and an impact parameter, there's no non-zero Poisson bracket between those.
Not here. No.
Just spins.
Yeah.
Yeah. Okay.
Would it be difficult to just write on the board the Poisson bracket explicitly? Since this has now been asked several times?
Yeah. So if you wanted this guy, for example, you might
take this up temporarily. Nope, not that one.
Like something like this, right?
I think now it's going to be hidden by the board if you don't travel up or down.
I'm going to go up it.
Yeah.
And this guy is going to look like, relativity.
It's not helpful. Sorry to have suggested it. And which one can I raise? Nope.
Well, I mean, for myself, that's okay. I know what
You don't
mean.
need to.
Okay.
Yeah, but then I guess. So, and you mentioned you kind of explicitly checked it at tree level.
Yeah.
And even at linear and spin was the example you gave in the slide. But
yes.
then you're also claiming it's all orders in G.
Yes.
Is that claim just at linear and spin or at all orders in spin?
We've checked it to linear and spin.
Okay.
As I said, the next thing to check is to really go beyond linear and spin.
Okay.
Yeah.
Thanks.
Sean's got a question. Also, maybe let's do Sean and then Carlo, and then anyone else from online.
So in terms of, can you say a little bit more about motivating why the minimal variance would be the one, right? You usually think that the domain of validity is where, your H bar is much smaller, right? Whereas like factors of 2 or whatnot don't matter.
Right.
So in that context, something with a little bit more variance would satisfy the fundamental assumptions just as much. So why is the minimum one the one?
Well, one motivation was that we wanted to generalize the iconium, which is an example of an object that's supposed to be classical, and one of the principles that it seems to obey by looking at the examples is these relationships between tree amplitudes and loop amplitudes, and minimal variance seems to give you these same constraints in other situations. So we just asked the question, can you apply this to other situations and find similar kinds of constraints that will give you some object that has the kinds of properties that you want? I would say it's not it's a necessary but not sufficient condition. As you say, you don't have to have, it's not necessarily going to give you the thing, but if you have a guess, it had better satisfy, right?
And then online, we have a question from Carlo.
Yeah, sorry. I just wanted to understand a bit better how the information is packaged between the chi and the terms that you were showing where you compute radiation reaction. So the chi, what you call chi, is somehow the iconal, but without the radiation reaction. Is
so here?
Yeah. For instance, if I understood correctly, this derivative of chi that you have in the second line in the equation that does not contain the radiation reaction, right?
No.
So okay.
That's just a conservative piece, and you could compute it without the. Well, in fact, in the paper we compute it before we add the applied particle amplitude.
Right. But then you say that chi also has an imaginary part because it was the one giving you the normalization, right?
Yes. So you mean?
I mean, later on, I remember you commented upon the normalization of the state and that it.
This. Yeah.
This just seems a bit strange to me, right? Because for us, I mean, the fact that chi is an imaginary part is really the same thing as saying that the real part of chi contains the radiation reaction. So it's a bit strange that, that your chi does not have the radiation reaction but has the imaginary part.
I can see that Donald was very eager to answer your questions.
Please, of course. I mean, it's just confusing.
Yeah, that's a good point. I think what's going on here is that the computation that Nathan just sketched, you would get a real part multiplying that because we're computing an expectation value. So there's something from the left, there's something from the right. When you add them up, you're going to get a real part, and then you'll get the term you're getting from the imaginary part. In our case, is coming through the M5 here. So I think.
Oh, I see. I see. Okay, so to clarify, the chi usually is just the conservative icona somehow.
No. It's the same chi as you've got. So it can have an imaginary part. But if you want to compute the delta p out of that chi, so you'll get this term involving the derivative of chi, but you're going to get a derivative of chi plus a derivative of the complex conjugate of chi, which just gives you the derivative of the real part of chi in the computation of the radiation reaction. So we need to, so we're bringing down this M5 from this coherent type state to give you the actual dissipative part of the radiation reaction.
I unfortunately hid that in the dots in the when I was sketching this calculation here, which I probably should do.
I see. And maybe just a quick, very quick follow-up. So then you were saying the integral of m d mu m is hard. Later on, or was it m?
So if you're trying to compute the radiation reaction in general, you mean? Yeah.
I mean, later on, remember there was another integral you said you.
This one. Yeah. So these brackets hide the integrals that we would otherwise need to do, and
I mean that involve the wave
packet. We're able to do them by stationary phase, which is very nice. But in the second case, in complete generality, I don't know how to do them. I don't think you can do them by stationary phase, Donald. You might. I don't think
you mean from this expression you cannot obtain the 8 minus 5 sigma squared divided by.
Right. So you can plug in, say, the tree level amplitudes to this guy, and then you can do the integrals of that order, right? Or maybe you can plug in the a one loop and do the integral at that order, maybe. But this guy at the top, we didn't do perturbatively order by order. We just did by stationary phase. And I'm saying we just can't do that for this second guy, unfortunately. But yeah, perturbatively order by order. If you're determined enough, I guess you can.
Okay, thanks.
Looks like Zvi has the next question.
Yeah, hi. Yeah, thanks a lot for that very nice talk. Maybe you could go back to the formula for the spin kick in terms of the iconal phase. So a couple of years back, we had a paper also with a formula that's not exactly the same, but it's similar. Can you comment on the differences?
Yeah. So, you guys have got this spin-orbit coupling piece that you call DSL that is apparently missing from this formula. And, in some sense, the first few terms certainly agree with what we've got, but really we need to do a slightly more detailed calculation to find where that piece is. It certainly looks like if you go to the right frame, these DSL terms will match something that we've got here, but unfortunately haven't fully finished the calculation to show.
Maybe one other question. What spin are you using? Is it the covariant or the canonical?
The covariant.
Okay. Right? But yeah, then there should be a difference. But
you also should be able to boost from what you guys have got.
Yes, that's right. We should be able
to, we can make this comparison, which is something we're trying to look into. Yeah.
Right. Okay. Yeah, that sounds interesting. Anyway, we should. Well, I guess I'm not there, but if I was there, we should talk about it. But maybe others. Demetrius might be there. If you're in the audience, Demetrius, you can raise your hand. Okay.
All right, an assignment has been passed on. Other questions, comments, discussion? Any questions? Looked like there's a question online. Yeah, please go ahead. You're muted if you're speaking.
you wrote the iconal with spin. You wrote up to the linear term in spin, correctly?
Yes, in the paper we just computed it up to linear instead. Yeah.
And that agrees with the calculation of Guevara, Okirov, and Vines at the level of the at that level or not?
Yeah.
But do you expect that if you compute higher order in spin, you get the same result that they get, or not?
I would hope so.
Okay.
Haven't computed.
Okay.
This is somewhat a minimal proposal in the same sense as the radiation part is, but I'd hope that if we compute it, we should get the same thing. Yeah. You know, again, up to frame choices and stuff like this, we'd hope that we'd match the literature.
Okay, thank you.
I'll take chair's privilege to ask another oddball question. So it's a little more philosophical, but you've started with a classical problem, so to speak, moved into the quantum realm, and then you use the minimal variance condition to sort of recover classicality. And this seems to be what has generated for you many, many interrelations. So it raises the question, if you hadn't gone first into the quantum realm, right, are these kinds of interrelations natural to understand from just a purely classical perspective?
No, I don't think so. You know, I think the key point is that I have to go back quite far. Well, I think it's probably the easiest. Yeah. So if you look at these guys, for example, on the bottom, right? This is roughly telling you that part of this one loop amplitude gives you no new information classically, right? Which tells you you shouldn't bother computing it if you're interested in the classical stuff. The dumb way to do it would be you calculate it, you do all your loop integrals, you write down the answer, you collect it all, and then, you know, look at all your scales and all that, and then you take h bar goes to 0 at the limit, and that's really inefficient. What this tells you, and what the minimal variance relations tell you between amplitudes, is that there are a whole bunch of amplitudes that you just never need to compute, because you can just recycle all of the old ones. That's where really the classical physics is. So I think that that's philosophically the goal, or the purpose of these relationships. And I don't know how you could see them classically, because they're talking about quantum objects.
Right.
Yeah.
Thank you. Donald's got a comment or question.
No, I just wanted to follow up on that. So yeah, I think it's an interesting thing. So for example, you know, these relations that Nathan's been talking about here also apply for 5-point amplitudes. You know, these are amplitudes of massive particles radiating off some stuff. So 5.2 loop amplitudes are very interesting at the LHC, for example. They're not so different; they're a bit different, but you know, but the structure that we're seeing here, we'd expect to hold for at least some of these amplitudes. And you can then use these sort of ideas as a check. If you've computed these amplitudes, 5 points for the LHC, that's a difficult computation, but if you expand them out, they should have, you know, they should have the structure. So it provides some information for people who have no interest in this topic.
Yeah.
Interesting. Yeah.
Oh, another comment? Yeah.
Another question. So you talked about the deflection and the spin kick. What about the waveform? Did I understand correctly that in your formalism for the waveform, all you would need is again just a 5-point amplitude?
Yes.
To any order in G.
Yes. So the full 5-point amplitude.
Yeah, but to any order in G, you don't have to look at higher, more than one graviton emission.
Well,
okay.
Yeah, that's the proposal.
Yeah.
If you want to say, for example, psi 4.
Yeah, no, from the world line perspective, that is also what I would expect. But I heard, I mean, there were also other opinions raised from the amplitude side for that. But you would now say the 5-point is all you need.
Yeah.
Okay.
All right. I think
and the 4-point.
I think that brings us to the close. Is there one last quick? Yeah, please go ahead, and then we'll get coffee.
Yeah. So thanks for a nice talk. Just to follow up the earlier philosophical question. So in terms of classical physics, is there anything new we can learn from these relations?
I guess the most interesting thing from my perspective is that you know, the idea, the core idea is that, you know, if you know the classical parts of the 5-point, the classical parts of the 4-point, you can kind of just compute everything that you might be interested in, right? But I can tell that Donald's got a different idea. So.
Yeah, sorry. Well, one thing that is very different from this perspective is how we're formulating the radiation reaction. Right? So, for example, Nathan showed that the impulse is given by two terms, one of which you compute by stationary phase. It's sort of roughly speaking the conservative part, and then there's this other part which is coming from this 5-point amplitude. Now, the conditions on that, as Nathan is saying, are things that we haven't really explored in great detail, but it looks to me like there's some integral differential equation, which is capturing that radiation reaction. I've not seen radiation reaction expressed that way before, so yeah, I mean, I think it provides a different perspective on some things. But of course, the final answer is supposed to be the same.
No, I think it would be quite interesting to track down what kinds of purely classical statements this might imply. But all right. With that, before everyone heads off, let me just add there's been a shuffling for the next session. Satya will speak first, just so you're aware. And with that, let's thank Nathan one more time.